Welcome back, everybody. So now we are going to go to part 9 of the lecture. And I'm going to first ask you a question, because I was told you like clicker questions. So let me just do that. And here it goes. So do you remember the logarithmic merge trees, right? So when we have this online indexing, where you keep merging and merging and merging the indices, you have these files of increasing size in power of 2, right? Size 1, size 2, size 4, size 8, and so on. And so if you call them like I0 for the standard size, I1 for double the size, I2 for quadruple the size, and so on, and you observe the system over time, and you look at what files are currently here, right? Among these possibilities, what are possible states? Meaning that you look at a certain point in time at the system, and you see, for example, there's only file 0, or maybe there's files 0 and 4, or maybe there's files 1, 2, 3, 4. So which of them are possible as a state of the hard drive, state of the files that are found? These are the possibilities. Oh, actually, I can show you. These are your answers. You can then decide. And some people agree. 0, 4, you have more disagreements, but you cannot have 0 and 4 at the same time, even though that disagreement is actually decreasing. Now 1, 2, 3, 4 no longer has a majority. There's more people disagreeing on 0 and 4. You can still change your minds. Now 0 is no longer unanimous. Okay. Still have a chance to change your mind. 50% now. Okay. Well, it turns out that all of them are possible. And the idea is that if you remember, you're basically counting in base 2, right? If you look from the left to the right, like the least significant bits are on the left and the most significant bits are on the right. So you read right to left. You first have 1. When you write I0, that's basically 1. Then you have 1, 0, which is I1 and nothing. Then you have 1, 1, which is I1 and I0. Then you have 1, 0, 0, which is I2, I1, and 1, 0. And basically, what I'm asking is, what are possible sequences of bits for numbers in base 2, right? And the answer is any. Any sequence of bits is a number in base 2. Who agrees? Right? So we have all these combinations are actually possible. Okay. I'm going to move back to the slides. Okay. Now I have this new clicker, so that should now work. And my mystery is solved because I was wondering, like, how is it so? That's actually the battery. Now I know. So what have we seen so far? So we've looked into Boolean retrieval, which means that we have a set of documents, and we consider each document to be a set of words. And then we have a Boolean query with and, nor, not, and or, and we retrieve a subset of the documents. Then we saw, again, the level of abstraction set of words means that we consider documents to be vectors of Booleans, right? Zeros and ones. That's the set of word semantics. And now it does it again. Okay. We have the standard inverted index. That is the most ancient form for the Boolean retrieval, where we just have a list of terms called a vocabulary organized in the data structure. That is a B+3, and that's called a dictionary. And every leaf of that tree structure points to a postings list. And in every postings list, you have first a count. And now we know it's called document frequency, the purple cell. It's the number of documents containing the term. purple and the black letter, a black digit. Then you have the postings that are sorted by document ID. And now you look at it maybe from a different perspective, because you know the sorting is the same for all the terms. And this is why you can actually do the intersection and union for the Boolean retrieval by concurrently traversing the list, right? And all the other indices or many other indices are variations of that, right? You can add positions, you can index pairs of words instead of terms, you can index permutations, you can index grams, k-grams, you can add term frequencies in the postings, and then you can implement cosine distance to accumulate evidence and so on and so on. So now you've seen all the variations of that index, but this is basically the skeleton on which everything is based. So, you know, we can have hash tables and trees for the terms. And now we can even throw graphs in there because you've seen these small worlds indices and IVF flat, right? So you can have all of these accelerating structures. And then that's more recent. It was just a few weeks ago, we started ranking the results, right? In Boolean querying, you don't rank anything, it's just a subset. But actually, in a search engine, you would like to rank them, to score and rank the results. So now you have a ranked subset of documents. And typically, what has become popular with search engine is you return the top 10, and then the next 10, and the next 10, and so on, even though apparently not many people actually go beyond page 2 or 3. Then we changed the abstraction and replaced the ones and zeros with actual numbers. And the reason is that we switched to bags of words, right? So now we do care about the number of times that a term appears in a document. That's called the number of occurrences. And that gives us a number of times. So now you might expect a vector of integers then, because you count, so it's integers, but in fact not, because you renormalize, right? So if you renormalize to 1, then you're going to end up with this. And the other reason it's not going to be integers is that you multiply the term frequency, the TF, with the IDF, right? And the IDF is the log of n over the DF, and that is not an integer anymore. So this is how you get vectors of numbers. Non-negative numbers in our case, it's the first quadrant. All right, so again, it's a simplification because what we do not have here is the order of the words, right? We have the number of occurrences, but not the order of the words. That would be a positional posting and a positional index. All right, so now we've seen everything, right? The sets of words, the bags of words, the lists of words. So you see, you just pick whichever abstraction you prefer based on what you are doing. Now we looked at the vector space model, where if we have vectors of non-negative integers, we are basically in the first quadrant of R to the power of big M, where M is the number of terms. It's a very high dimensional vector space. And we can even store that in a vector database and use SQL in order to filter by distance to a specific query vector and so on, or order. So now we are going to evaluate the system and look at metrics that tell us how good our system is. For example, we want to know what effect does it have to use stop words? Does it improve our system? Or should we exclude numbers from indexing? Should we just index words and we don't have phone numbers or whatever? Or is it a phone? It's like vibrating now. Is there an incoming phone call or something? I don't know. Or maybe that's the battery again. What is the best value of R for champions list? For example, if you adjust your parameters, you need to evaluate how good they are. Do you use stemming? Do you use lemmatization? We saw it depends on the language, right? Stemming is actually good for English. For languages like German, Italian, French, you prefer lemmatization because there's a lot of conjugation. Should you weigh, I'm not sure there's a T here. Should I weigh the query terms? Like, do you care about the term frequency of the terms on the query side, right? On the document sides you do, but on the query side, do you as well? So these are all open questions. Should you renormalize the scores with L2, meaning that you renormalize the vectors to 1? That's a lot of questions, actually. Which document weights should I use? And so on and so on. Another aspect is that you want to optimize the relevance to the user, right? What you want to do when you answer these questions, you want to return relevant documents to the user, right? If you look on Bing, you look for a website, you want a relevant website. So the idea to evaluate, it's like in machine learning, you need training data or you need evaluation data. So you need to gather that data. So the way it works on a very high level perspective, you have a set of documents that you use for this evaluation. So for coming up with an evaluation scheme, you have a collection of documents that probably is going to be smaller than the internet, like a smaller one. And you have a set of information needs, right? A set of queries that you can ask the system, except that here you formulate them in English. Like it's the information need is what you have in mind when you look for it. And so you have a collection of documents, and what you need to do is gather a few people that you might pay, and you give them a document and you give them an information need, and you ask them a question, yes or no, is that document relevant to this information need? And that person is either going to say, no, it's not relevant, or yes, it's relevant. So here you picked one document, one information need, but you need to do it with different documents and different information needs, right? In fact, if you take all combinations, it's the product, right? Every combination of document and information need gives you a yes-no answer. It might even give you several yes-no answers if you also have multiple people that evaluate that. They might also disagree, right, on whether it's relevant or not. So basically, you need many documents, many information needs, and many people, and then you just ask them as human beings, like, is that relevant or not relevant to the information needs, right? In the very early days of information retrieval, that probably dates back to the 60s, maybe 70s, we didn't have the computing power that we have today. We didn't have crowdsourcing and so on and so on. So we needed to come up with smaller collections. So for example, one of the early ones that was called the Cranfield dataset had a bit more than 1,000 documents, 225 information needs, and then they invited a few people over and they put relevance judgments, right? And that basically means that they roughly gave 200,000, maybe 300,000 yes-no answers, right, if you have all combinations. And then, of course, they improved with another data set. It's called the Trek data set. This one had almost 2 million documents and 450 information needs. At some point, you might want to become sparse, by the way. You might not actually do all combinations, but only a subset of them. And again, you have human beings that say, yes or no, I think it's relevant or not. By the way, especially in the early days, they were not asking random human beings, right? They would have a data set, I don't know, based on, I think what was popular at the time was law, so legal data set, and also aeronautics data sets on that I think they used back then. And so they ask experts to tell you yes or no that's relevant for the information need. So at the end of that, what you have is just some data sets that tells you whether or not documents are relevant to information needs. And that's completely independent of your information retrieval system, right? At that point, we don't have yet an information retrieval system. However, if we now have an information retrieval system, I can use that information to check against that. Like, how does my information system behave in the way it returns the results? Does it match the expert judgments that you have right here of the domain experts? So just to be clear, the difference between information need and query is that the query is what you type. It's the words that you type on your computer. And that might be in multiple things, right? If you type ETH Zurich, then maybe Alice is searching for a higher education institution for her kid, right? We see a lot of them actually in the Mensa now, so they're getting younger and younger. Or maybe Bob is searching for Ethereum cryptocurrency in Zurich, Kansas. Or maybe Carlos is searching for the extended trading hours, ETH, on insurance stocks, Zurich, right? So you see that there's a difference. And it seems obvious when you look at the query, but if you think about it, no, it's not. There is not such an obvious map between the two. So basically, that also works in the other direction. If you have a specific information need in mind, the way you are going to map it to a query might actually differ, right, depending on how you tweak. And so in the early days where you actually were forced to enter your queries in Boolean search, especially the legal systems, people were very fluent at that. There's a lot of people who basically trained in such a way that they were very, very good at writing queries. Right? But it reached some limits, right? For example, in the Boolean systems, the problem you have, and that customers experienced, is that either you have too many documents or too few documents. It's very, very difficult to have just al dente, right? The right number of documents in the outputs. So this is why we came up with other systems. By the way, now with LLMs and ChatGPT, this is becoming blurry, right? Because now, if you have an LLM, you can also directly enter your information needs expressed in English. But again, it's not that obvious because now there's a whole buzzword of prompt engineering on how to actually write the prompts to the engine. So again, you're back to square one. You still have the problem of how do you map what you're looking for to what you're actually going to put into the system. Okay, so now I'm going to go into metrics that we can use based on that, precision and recall. And as this picture illustrates, we are basically going to have 4 groups, 4 colors, yellow, red, blue, green, of documents classified in every query execution. And based on that, we are going to compute the metric. So the idea is that I put the green in light and the red in darker so that you can see the difference, everybody. The idea is that if you look at just what is returned, you have on the left the relevant documents in green, and on the right, the not relevant documents in red. So the precision is basically telling you in what I return to you, how much of that is actually relevant to you. If it's very precise, then that's going to be all of them. I only gave you documents that are relevant to you. If you have bad precision, it means that I only gave you garbage, and these documents are totally useless. So the precision is the division of the total number of relevant returned results divided by the total number of returned results, relevant or not. What is the precision here? On that example? Anybody? Okay, say it all at the same time. I know you know. Say it all. 1/2, exactly. I knew you knew. All right, so the true positives, we call them the true positives, the ones that are relevant and return. And that gives us here, please. When I click, it's going to jump three slides forwards, I'm sure. Okay, 50%, indeed, 1/2. Now, what's the precision? 100%, yes, because everything is relevant. And now, what is the precision? 0%, right? Now we just return garbage. Okay. And now I'm back to the same battery problem. This is, okay. What is the precision here? Say it again. 80, yes, 80%. 8 divided by 8 plus 2, 8 divided by 10. So yes, 80%. Okay. So now let me complete. I promised to you there will be four colors in total. So now I'm adding what is not returned. That's the negatives. The positives is what's returned. The negatives is what not returned. And what's not returned can also be relevant or not relevant, right? So I have 4 categories, 2 by 2. So now if you look closer, let's look at these 4 categories. This is what I return to you and that you care about. This is what I return to you that you don't care about, I shouldn't have. This is what I did not return to you, but you would have cared about it. So I should have returned it. And this is what I did not return to you, and you also don't care about it. So basically, this was done right. This was done right. This is what I should have returned, but I didn't. And this is what I shouldn't have returned, but I did. Right? So these are the false positives and the false negatives, and this is all good. So now that we have these 4 categories, I can introduce another metric called the recall. The recall is also a division. It has the same numerator. It's also the number of true positives. And I'm dividing that by the total number of relevant documents. It means that I look at the whole collection. I look at all the relevant documents, the ones you would have cared about. Right? Of course, it's a theoretical experiment. For example, if I say all of the websites that are relevant to information retrieval, there's no way in practice that I can tell you, right? It's a theoretical experiment. Except if you have the Cranfield data set or the Trek data set, because then you do have that. But again, the relevance, the recall is the division of the true positives divided by all the positives, everything we returned. So the recall here is, everybody at the same time, 1, 2, 3, 50% exactly. What is the recall here? 100%. What is the recall here? 0%. It's written in here. Okay. What is the recall here? 67, right? 66.6666. Okay, 2/3. Okay. Now, so I told you false positives, false negatives. So the one on the top right and the bottom left, I don't like because these are mistakes, actually. They always happen. I mean, no system is perfect, but these are the ones we don't like. Now, it turns out that if you go to the machine learning lecture, that's not new to you because that's also used there. We have the type 1 error and we have the type 2 error. Now, I don't know for you, but I never remember what is type 1 and type 2. No matter how I try, it's been years, I never remember 1 and 2. So I just say false positive and false negative because then I know what I'm talking about. Who is able to spontaneously type 1, type 2, you immediately know what it is? It's the same, right? It's the same for you. Okay. So I just say false positive and false negative because it's more intuitive to me. And then we have, of course, the true positives and the true negatives, and this is the part that is actually the correct part of the system. Now, if we classify system based on that, we take the track data set or the Cronfield data set, and then we execute queries like this, and then we know what's relevant and not, again, because of the domain experts that told us what is relevant or not. The size of the collection, that was this 1,400 or 2 million, so it's a limited size. And now I have that. So now, if you look at that, who sees that this is a high precision system? It's a high precision system. You need to look at the upper part because what you return is mostly relevant. There's not a lot of non-relevant positives, right? Not a lot of dark reds. Now, this is high recall. Who sees that it's high recall, right? Because you have very good. So you have a relevant document, and most of what's relevant I actually return to you. It's the blue parts on the bottom left. There's not so many of them. Now, the trick and the challenge for a system is to strike a balance between this and this, right? In practice, getting the two of them is almost impossible. That just doesn't work. And you need to ask yourself, what do I care about? Do I want this or do I want that? It's a compromise that you need to make, and you need to make a decision on what you want to achieve. Okay, so I'll come back to how you can mix them. Precision, recall, turns out that there's a third one. In fact, there's even others, but there's a third one called specificity. Does anybody know what it is, specificity? Okay, let me tell you. It's like the recall, but on the non-relevant part, basically. The specificity is basically, you need to look at what you don't care about, and in what you don't care about, how good was I at not bothering you with that? Right? It's basically the specificity. How good was I at not returning to you stuff you don't care about? If you think of it, it's just like recall, but on the right instead of on the left. So what is the specificity here? 50%. Okay. And here? 100%. It means I didn't bother you with anything you didn't care about. And basically, you see the link with precision, you would have basically 100% precision here if you have 100% specificity, because you don't have true positives. What's the specificity here? 0%. I basically threw everything you don't care about, I threw it at you, basically. I threw the whole internet that you don't care about at you. Okay. What is the specificity here? It's roughly 60%, right? 4 divided by 12. Yeah. Did I do it right? Actually, could I have made a mistake here? You see, so 4 plus 6. No, it's 10 in total. So 4 divided by 10. Sorry, 6 divided by 10 because it's the yellow part that is on top. Yes, 60%. Ooh, I got it right. All right. In fact, it's good because it forces me to slow down, make sure that I'm not going too fast in what I'm telling you. Okay. There's yet another one called accuracy. Who knows accuracy? Accuracy is overall what you did right. So it's basically the true positives and the true negatives, the top left and the bottom right, divided by everything. So it's everything you got right. In that case, the accuracy here is 50%, right? 8 divided by 16. Here, what would be the accuracy? (67), right? It's the 2/3. It's all the part in the diagonal, the matrix diagonal, divided by the total. Who knows that accuracy is a very bad metric? It's one of the first things they tell you in machine learning. If you use accuracy, you're wrong. You should be using other metrics. But I'll come back to that, why it's actually not a very ideal measure. Here, the accuracy is, everybody, 1, 2, 3, 100%, just to get you used to spontaneously seeing that. And here, the accuracy is 0%. Okay. Now, imagine that I want to cheat. Imagine there is, I don't know, an exam, and I'm supposed to build an engine, and I get a top grade if I have an accuracy of 100%. But you're lazy. What are you going to do? Well, technically, it's not foolproof, but basically, you can hack accuracy by never returning anything. Just enter a query, results, nothing. That's as lazy as it gets, right? This is super easy to implement. But you need to understand why it works, because that wouldn't work on any structure here. This is because in practice, you're going to have many more documents that are not relevant than documents that are relevant. If you're doing a search, you're probably interested in 0.0000001% of the internet, right? So it means that if you don't return anything, it's very, very likely that most of the internet is not relevant. So when you compute the accuracy on that, you basically get 99.99999%. So you can basically get away with it. You're just lazy, you don't implement anything, and you have almost 100%. And again, that comes from the discrepancy between the two labels, relevant, non-relevant. For whom is that here? So this is one of the reasons why it's a bit dangerous to use accuracy, because that can be tricked in this way, so it's not optimal. Okay. Now, how do you hack recall? How do you get 100% recall? You return everything, exactly. If you return everything, then you basically have full recall. You might also return garbage, right? But technically, you get 100% recall because since you returned everything, there is nothing to add on the true negatives. For whom is that clear? Right? So you see the recall alone is not necessarily enough to do it. So now it's critical thinking, right? We have these metrics and we ask ourselves, are they actually useful? Are they actually relevant? Right? So the recall is going to be 100% even if I return garbage. All right. So we need to merge the two, precision and recall, which is done in practice. A naive idea would be to just take the arithmetic mean, right? P plus R over 2, precision plus recall over 2, and that's it. The problem is that very often you have systems that have high precision and low recall, or systems that have high recall and low precision. And the problem is that once you do the arithmetic mean, whichever is low does not influence the average because it's negligible. So it's going to be just the one that is done right that influences the average, and the one doesn't tell you anything. But there is a trick to solve that, because you know that there's different ways of computing means, right? Who knows the geometric mean? Right? It's the square roots of the product, right? It's technically the same, but with a log difference. Who knows the harmonic mean? Some of you. Whoever took an electronic lecture and resistors, right? Resistor in stereo, parallel, and so on. You probably remember that formula, right? When you have to compute the equivalence resistance of two put in parallel. Well, that's pretty much the same thing. So The harmonic mean means the inverse of the arithmetic means of the inverses, right? So it's this, and if you just rewrite it differently, this is what you get. And again, if you've done electronics, then this is something you should already have seen. And this actually works better because in that case, it's a true merge of precision and recall without losing the influence over the metric of the one that is negligible compared to the other. So that's a harmonic mean. And of course, that's if you take the equal weights, but if you vary the weights, you have different weight for precision and for recall, you can have a factor alpha, and that's called the F measure, right, based on the harmonic mean. This people kind of like, right? You can actually compute the precision and recall in that way. If you have alpha equals 0, then technically F0 is equal to, what is F0? Okay, say it all at the same time. F0 is, exactly, it's the recall. And F1 is the precision, exactly. So you have, if you completely at 0, you have the recall. If you're completely at 1, you have the precision. And in between, you have the slider that you adjust between the two. 1/2 being the standard. Okay. And you can adjust this metric basically based on what you care about, and that probably depends on the application of your retrieval system. Are you scared of true positives or are you scared of true negatives? So now we are going to use precision and recall, but in ranked retrieval. So now it's going to be a bit different because precision and recall, that works well in a Boolean retrieval system, right? Because I have what's returned and what's not returned in a Boolean system. But in a ranked system, it's not about what I return and what I don't return. It's about the order in which I return it. Because technically, I mean, I don't know if that would actually work, but if you type a search in Google and you click hitting next, at some point you might get the whole internet, right? If you keep going. Probably it stops at some point. But technically, if you just rank, you always get the whole collection. It's just about the order in which you do that. So can we apply precision and recall? Of course, the answer is yes, because otherwise I wouldn't have a part titled that way. So I'm going to show you how you use precision and recall on with the vector space model, with a ranked retrieval system. The way you do that is that you introduce a two-dimensional plane like this. Precision is on the y-axis and recall is on the x-axis. And we are going to boot the ranked retrieval system, and we input a query, and we start reading the results. The first result, the second result, and so on and so on. And every time, I compute the precision and recall as of the current status. So if I start, I don't have any query at all in the system. I didn't receive anything. Where is my precision and where is my recall? What is the recall if I haven't returned anything? It's 0, right? The precision, well, it's kind of undefined, but you can basically, let's say it's 0 and undefined. Now I have my first document. My first document is returned. Let's consider the two cases. In the first case, I have a relevant document. So my precision at that point is 1. It's 100% because so far I only got relevant documents, and my recall is 0.0000. It's just a tiny part of the internet. It's just one page, right? So basically, if you look at where you are on that graph, do you agree that you're basically here? Who agrees with that? Right? So far, you have very little recall because you only got one result, but you have 100% precision. If it's not relevant, then you're there at 0, 0, right? So now let's just assume that I have a relevant document. Now comes the second document. The second document could be relevant or not. If it is relevant, then I have a precision of 100%, and a recall of still very small, but a tiny bit more, right? So basically, I go a tiny bit on the right, but still at 100%. Now, if it's not relevant, what would happen instead is that my precision would be 1/2. So I drop in precision, and my recall would remain the same, right? Who agrees? So these are the two possibilities. So let's keep that, imagine. Now, a third document is not relevant. So my new precision is 67, right? 2/3, and the recall remained the same. So you see, two things can happen. Either I go a bit down, constant X, I just lose on Y, or I go a bit to the right. So now that's losing precision, non-relevant. Now I gained a bit of precision because now it's 3 divided by 5 instead of 3 divided by 4. So I gained a bit in precision, and I also gained a bit in recall, right? I have one more document. Who agrees? So let's now continue. Every time it's not relevant, I go down. Every time it's relevant, I go to the right and up, right? So relevant, 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 not relevant, not relevant, not relevant, relevant, and so on and so on. Who gets that? That's how we do it, right? And we just get some curve like this that gives us a precision recall curve. This is the trick. Now we do a bit of smoothing because technically this would be hard to manipulate. So what I do is that I cheat and I'm going to build some stair function like this. I basically draw some sort of hull to it that looks like this. Who is with me? Okay. So I do that. Note that this is not something you can implement in a streaming fashion because you would need to know the future. Right? You cannot know in advance. For example, this is just to make you aware that this is not easy to implement. Right here, basically, you would have the curve. But when you're here, you don't know yet that you are going to arrive here. Right? You can only do it a posteriori. You need to go all the way here, and then you know that it goes to the left. Just a remark. So now we have this curve, and technically, you always get, if you go all the way to the whole collection, technically you get some curve like that goes from full precision, no recall, to full recall. That's when you return the entire internet in your search results. But of course, the precision now is very low because that's almost only things you don't care about. What you typically do is that you interpolate the 10%, 20%, 30%, and so on. You don't take all the points. You only say, okay, what when I have 10% of the internet, when I have 20% of the internet, and so on, right? So that's basically it. Or maybe you stop, you don't need to go the full internet. Maybe you stop when you are satisfied and you believe you have most of everything you wanted to have. But basically, that gives you 11 points because you remember 10 intervals, 11 points, right? 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. That's 11 in total. Okay, that's called 11 points interpolated average precision. Right? Now, an awesome search engine that I would like to pay for in order to have, do you agree it would be like this? It keeps returning relevant results, keeps high precision, and I just increase the recall and never lose precision. That I would pay for. That is awful. It's basically an engine that keeps returning stuff I don't care about. This is bad, right? Okay. Now, what people also do is that this is what we've done for one query. I took one query, one information need, and I put that curve. Now, in your Cranfield data set or the Trek data set, you have other queries and you have other information needs. So you can plot the curves as well. So you get plenty of curves like this, right? So what you can do is that for every query or every information need, you can compute the average precision, right? So you basically have some cutoff on the right, then you have the average precision. And then you again compute an average, but across the queries. It's the average of the average. But of course, an average doesn't sound very nice, so they say mean average, which is the same thing, right? So it's the mean average precision, and that adds a third dimension with the information needs, right? Technically, if you think about it, you just plot the curves along a third dimension. That's basically the volume that you have below that curve. Who sees that? It's the volume. You want to have as much volume as possible. You want to be as close to 1 as possible. Who sees that? There was no raised hands. Who sees that I want to see the volume? Okay, very good. So it's the mean average precision, which is not surprisingly summing everything, and then you divide twice by the cardinality. Okay. Next, there is something called the R precision. What is that? Imagine you have this ranked retrieval system, And imagine that at some point, it turns out it's a huge coincidence. I happen to have K relevant documents, and I returned the top K, and I'm looking for the case where I have exactly the same precision and recall, right? So I would like to measure when that happens. In other words, I'm just crossing, I have my 11-point interpolation curve. I'm drawing the y equal x line. It intersects somewhere with my interpolated curve. That gives me what is called the R precision. I basically wait until the point that my precision is equal to my recall. Now there is a theorem in mathematics that tells you that that has to exist, right? If you have a continuous function that starts above and finishes below, it has to cross the line at some point. Fortunately, it's not a mathematics lecture because a mathematician would tell me that this could be not necessarily exactly one. But anyway, that's almost. So basically, when you intersect the curve, you have the R precision. That is also a good measure of your system. Do you realize that if I have a very good system where the curve is almost always high on the precision, then R will be almost equal to 1? And if I have a very bad system that immediately loses precision, then R will be equal to 0. Who sees that? Okay. Now, there is a last one that I like to explain with a metal detector. So imagine that you're on the beach and people lost Bitcoins, and you have a metal detector that is able to detect Bitcoins. And so you have a knob that you can turn that has the sensitivity. So basically, you might want to start very conservative. So you put the knob to minimal sensitivity, and you start walking around seeing if you find Bitcoins. But the problem is that it never beeps, right? So what do? Maybe you turn the knob a little bit, and I'm going to make it a bit more sensitive, right? So I increase the sensitivity, and then you might start detecting a few Bitcoins here and there, but still not enough. So you say, okay, I'm going to turn the knob a little bit more. I'm going to continue to increase the sensitivity. Then it's going to beep more. And then you become greedy, saying, now I want all the 21 million Bitcoins, so I want to find everything, and you turn the knob to maximal power. But do you see what's going to happen now? It's going to beep all the time, even when there is nothing. And this is exactly the way to look at this curve right here. It's actually inspired by electronics. I never remember what ROC means. It has to do with receiver output something. You can Google for it, you will find it. I just don't remember it right now. But the idea is that you start with the metal detector. At first, you're not very sensitive, but you're not very, the knob is at 0, but it doesn't beep. And then it starts beeping more and more and more. But the problem is that you start having false positives. So then it shifts to the right. So what you are plotting here is technically the recall and the specificity. Remember the recall and the specificity. Recall, we just call sensitivity, but it's the same thing. And then specificity is the mirrored. You just mirror it between the left and the right. So the idea is that this is something we love to have because you turn the knob a little bit and you immediately have Bitcoins. This is bad. So this is basically few false positives, lots of false negatives there. Here you would have few false positives in here. Here you would have a lots of false positives. So this is the summary, right? So basically, this is the sweet spot. We would like to, as soon as you turn the knob, it starts beeping, and it exactly beeps when you have Bitcoins. This here is not so good because it beeps basically all the time, and it doesn't even find any Bitcoins, just keeps beeping for nothing. So now, this is great. Who agrees this is great? Right? I turn the knob and immediately get Bitcoins. Here, I turn the knob, but I never get anything. So this is awful, right? Who would still pay for that metal detector? I would pay for it. Do you see why? It's very good at detecting Bitcoins. It's just that to detect them, you need to look at when it does not beep. You see what I mean? Just walk around, it stops beeping, oh, here's a Bitcoin. So in fact, it's great. This is what's awful. What's awful is when it's just randomly beeping and without any correlation, right? So just remember this metal detector story. This is how I remember that. This is just to scare you with some fancy machine learning, just to say that there's advanced methods, but fortunately, I'm not teaching machine learning. But yet you can basically extend the whole thing into very fancy papers and results, which leads me to the conclusion. There's plenty of metrics. You can measure also the expressiveness of the query language, the speed of the search. We talked with the indices, and so on and so on. And that's the last slide. I'm finishing exactly on time. Just checking that I didn't lose you. Now we are exactly on time with the schedule. I think last year we finished evaluation exactly on the same day. But just checking where we are, that if you're below 80, I will take more time for questions. Otherwise, I assume you're following and the speed is okay. Okay. All right. So thank you very much. I hope that even though you were not in Germany, you had fun today. And I hope that those who are in Germany are having fun. I'll see you next week. You have an exercise. Oh, you have a mystery game. So you will play with vector databases with PostgreSQL. And in fact, the TA team, and in particular Marco, prepared a mystery for you. And if you solve it, there will be prizes, right? I will let them announce what the prizes are. And maybe we'll give them on the last lecture. There will also be a big quiz game, and we can distribute the prizes, right? So try it out. It's optional, but maybe it's fun. So thank you. Enjoy your meal. Enjoy the rest of the day, the exercise, and I'll see you next week at 10 a.m. Thank you.